Okay, so what we're going to be talking about here is how we find the length of a curve. And hopefully this will make a lot of sense as we start talking about it, but just be aware, this is one of the easier ideas that we talk about in Calculus BC, mostly because there's just not an awful lot to it other than remembering a formula once it boils down to it. But let's take a look at what we're doing and kind of where this comes from. Let's say I was looking at this function right here, y equals x plus 2. Now to draw that function, I would just go up 2. Then from there, I would go up 1 over 1, and I would just have a straight line that looks like this. And let's say I wanted to know how long that line was from x equals 1 to where x equals 4 on this function. So I was looking for this length that I have right there. Now, you learned how to do this a long time ago in a math class by using what's called the distance formula. In reality, the distance formula is just Pythagorean theorem, where we have a, b, and c here, where c is the length of the side we're looking for. If I went a squared plus b squared is equal to c squared, I could find out what c was, because a, if I think about it, this point right here is the point 1, 3, and this point right here is the point 4, 6. A, if I find out, what I'm really looking for is how much the x values have changed by from x equals 1 to x equals 4. So that would be 3, and I would square that, plus, if I'm looking for b here, that's how much the y values change by on that same interval. So I would have 3 squared there as well, then I'd have c squared. And from there, you just found that the length of that particular segment of the line that we were looking for was the square root of 18. And as long as we're looking at a straight line, this isn't a big deal because I can always use Pythagorean theorem to try and find that. The problem is let's say I was looking at like the sine of x. Okay, now the sine of x is a graph from 0 to 2 pi that looks like that. Here's 0, here's 2 pi right there. If I were to ask you to find out how long that curve is, in other words, if I were to follow this curve along the entire time and find out the length of it, that's going to be a much bigger issue. The reason is nothing is straight on that particular line. Like there's curves all over the place, and that distance formula that we were talking about only applies to straight lines. So although there is a way to find it, it's not nearly as easy to see, at least immediately. But let's say, again, I've got my curve and it looks like this. Let's say I were to zoom in on a teeny tiny portion of that graph. So I'm just choosing this at random. Let's say I was to zoom way in on that portion of the graph. If I were to look at that, if I zoomed in enough, regardless of how curvy the graph is as I look at it from way far away, it would turn into a little teeny tiny line if I were up close. So it would turn into a little teeny tiny line, which means, and this is where this kind of gets interesting, at least I think so anyway, that I could use Pythagorean theorem, so I've got A, B, and C here, to find that teeny tiny portion of the line if it were small enough. In other words, just like we talked about before, if I could find out how much x changes by from one to another and how much y changes by as I go from one to another, I could use Pythagorean theorem again. The problem is we need this to be a really small piece, which means if I make it small enough, my A, my side A there, is just going to be a really small change in my x values, which we've talked about before. We call that dx. At the same time, my B here that I'm looking at is going to be a really small change in y. We would call that dy. And no matter what portion of the graph we zoomed in on, we could say that it would be, we would have dx squared plus dy squared, let's try that, dy squared, is equal to c squared. And again, that's supposed to be dy squared. Now, this next part you actually don't need to know, but I'm going to show you something that you'd like, why would I ever do that? And it hopefully, you won't ever have to do this on your own, but it makes this problem be a lot easier. On the left-hand side, if I wanted to, I could factor a dx squared out of both of those terms. Now, when I factor a dx squared out of the first term, that's really easy to look at, okay? When I factor dx squared out of that, I'd get 1. The problem is in the second term, there is no dx squared. Anytime you want to factor out something that doesn't exist in a term, the way that you do that is you leave the original term the same, and then you divide by what that particular thing is that we're factoring out. So in this case, if I had that, I'd have dx squared multiplied by 1 plus dy squared divided by dx squared, and that would equal c squared. So in this case, I could say that c is equal to, I'm going to rewrite it here, 1 plus, I've got dy over dx squared multiplied by dx squared, and then we would take the square root of all of that. Now, you'll notice that I'm taking the square root of this thing, and again, this is kind of complicated algebra, and it's not something that you're going to need to know for the AP test. But when I take the square root of two things multiplying together, I can take the square root of each of them individually, and I'm totally fine. So I get 1 plus dy dx squared. If I want to take the square root of dx squared, the squared and the square root cancel each other out, and this would turn into dx. Now you might be saying, okay, big deal, what did I just do right here? Well, that is how we would find the length of any teeny tiny portion of the curve. And let's say I wanted to find a whole bunch of teeny tiny portions and add them all together. Well, if I wanted to do that, whoops, and the squared only goes on the dy dx squared. Put the parentheses in the right place there. There we go. If I wanted to do that, we have a tool that adds up a bunch of teeny tiny portions. That is our integral. So if I do the definite integral from one number to the other x value of that formula that we just barely found, so the square root of 1 plus dy dx squared multiplied by dx, that will tell me the length of any curve. Now, that might have been kind of complicated, but in reality, the way that we find the length of any curve is this. We just do the integral from a to b of the square root of 1 plus whatever the derivative is of the function in question squared, and then we just put a dx on the end, and we've already talked about what that means. So if I wanted to know how long this curve is on the interval from 0 to 2 pi, I would just do an integral from 0 to 2 pi of the square root of 1 plus, I have to take the derivative here in order to use my formula, so dy dx in this case is the cosine of x. So I get 1 plus the cosine of x squared dx. Then I would just get that, and I would type that right into my calculator using Math 9. So I just push Math 9 on the calculator, go from 0 to 2 pi of the square root of 1 plus the cosine of x squared dx. And when I do that, my calculator thinks for just a second, and it tells me the length of that curve is 7.640, whatever the units are. And again, where it came from is kind of difficult, but the way that we do these problems is actually pretty easy. So like on this one, this is a little bit more complicated because I do need to do the integral from 0 to 3 of the square root of 1 plus, and then I just have to put the derivative of all of this in there. Now, in order to take this derivative, I am going to have to use the product rule for x squared times e to the negative x. So I go first times the derivative of the second plus the second times the derivative of the first, and then we would just go plus 2. So I would plug all of that in there, x squared e to the negative x times negative 1 plus e to the negative x times 2x plus 2. Then I would square all of that, and I put a dx on the end. And I'm not actually going to type that into the calculator. I know you guys can do that to find out what that length is. But in reality, the only thing we really have to find in these problems is what the derivative is, and then we just substitute that directly into our formula that we've talked about previously to find out what that length is going to be. And it doesn't matter how hard or easy it is to evaluate the function. I just need to know how to find the derivative so that I can plug it into my calculator. So one more, okay? Let's say I wanted to find the length of this curve on the interval from 1 to 9. I would just go the integral from 1 to 4 of the square root of 1 plus, I take the derivative of that, so I get dy dx is equal to 3 halves x to the 1/2 power, and then I just put that smack dab in there, just like that, square it, dx, type it into your calculator, and you have your answer there. Again, I think this is one of the easier ideas. Where it comes from is a little bit complicated, but that's not something that you need to remember, just how to apply this formula to find the length of the curve on any given interval. If you have any questions about that, please let me know.